Hi everyone. In this video we're going to continue on with section 5.3, which is talking about properties of rational functions. And the property that we're going to focus in on in this video is the vertical asymptote of a rational function. Okay? And so here's a theorem from our book about locating vertical asymptotes. It says the graph of a rational function, they call that rational function R, which is equal to p of x over q of x, where both p and q are polynomials, in lowest terms has a vertical asymptote at x equals r if r is a real zero of the denominator q. That is, if x minus r is a factor of the denominator of the rational function, in lowest terms, the graph of r has a vertical asymptote at x equals r. Okay, so that was a lot, right? And it might have been confusing, but the idea behind it really isn't bad. The first thing that we need to make sure we understand is the term in lowest terms. And what that means is once I've factored everything out and I can't get rid of anything or combine anything, so on and so forth. So in lowest terms means literally that it cannot be factored any further. Can't be simplified any further. So once we get it down into lowest terms, then it has a vertical asymptote, x equals r if r is a real zero of the denominator q. Basically what that is saying is that once you've factored it, once you've simplified it as much as you can, you find what the zeros are of the denominator, you find the solutions. So you set the denominator equal to 0 and you solve. That's the same thing that we did in the last video when talking about the domain. So what we did with the domain was we found where you get a divide by 0 problem, and that was what helped us find the domain of the function. We're going to do the same thing here. We're finding the zeros of the denominator, which would get us a divide by 0 error, right? And that's going to give us where the vertical asymptotes are, hopefully. So let's look at a few examples. The first one is x plus 3 over x minus 1, and then we've got one that's a little bit more complicated for number 2. So if we look at number 1, you first need to ask yourself, can we simplify this any further? The answer is no. We can't cancel out anything in the top and the bottom because x plus 3 and x minus 1 aren't the same thing. So we have our polynomial in lowest terms. Okay, so we set the denominator equal to 0. We want to see where we get that divide by 0 problem or error or whatever you want to call it. X minus 1 is equal to 0, and thus x is equal to 1. Okay, so that's where we get the divide by 0 error, and it turns out that the vertical asymptote of this function happens at x equals 1, and that's what I'm looking for. Okay, so not really complicated. I just need to find where the denominator is equal to 0. When that's true, that's where the vertical asymptote is. All right, so let's go to number 2, a little bit more of a complicated one. X squared minus 9 over x squared plus 4x minus 21. What we first want to do here is notice that I can factor the top, and it turns out I can factor the bottom. So the top can be factored into x plus 3 and x minus 3. X squared minus 9 is a perfect square, okay, and we can factor that. And then in the bottom, I have x squared plus 4x minus 21. So I need to think of two factors of 21 where I add them together to get positive 4, and then I multiply them to get negative 21. And it turns out that x squared plus 4x minus 21 can be factored into x plus 7 and x minus 3. Plus 7 minus 3. So 7 minus 3 is 4, or 7 plus negative 3 is 4, and 7 times negative 3 is negative 21. And so that's where I get that. And thus, I get some cancellation here. The x minus 3's sort of go away. And what I'm left with is x plus 3 over x plus 7. So where does the denominator equal to 0? Where does the denominator equal 0? X plus 7 equals 0, so x is equal to negative 7. Thus, the vertical asymptote of this function happens at x equals negative 7. Okay, so not too bad, hopefully. Here's some your turns. Again, try them out, see if there are any vertical asymptotes. And then if there are, tell me where they are. Okay, there can be more than one. In both of our examples, there was just one. There can be 0, there can be more than one, and there can be 1. Okay, so all choices there.